Welcome. In this video, we're going to talk through some calculations involving electrolysis and something called Faraday's law. So our goal is to use Faraday's law to complete calculations with respect to the following values. And these are values that might be given or values that we might be solving for. So one we want to consider is the number of electrons transferred, the mass of material deposited or removed from an electrode, the current, time elapsed, and the charge of the ionic species involved. And there's some important information that's given to us on our equation sheet, and that's represented over here to the right. So we have this equation, I equals Q over T, which we'll talk about on the next slide. You also have, this is given to you, Faraday's constant is 96,485 coulombs per mole of electrons. And you're also given this information that a volt is a joule per coulomb, just in case you ever need that. I also want to point out, sometimes on older versions of the AP test, I have seen them refer to something like this. They might say that you have 1 Faraday of charge. So if something refers to a Faraday would be 96,485 coulombs. I just wanted to say that just in case. I have a feeling this is, an older maybe terminology that I don't see them using as much anymore, but just FYI, if you see a Faraday, that's what that means. Okay, it's the amount of charge per mole of electrons. Okay, so let's dig into this equation right here, I equals Q over T. So this is an equation that describes current. So the current is the amount of charge per second. And again, this is given on your equation sheet. You don't need to memorize it. And the current we measure in amperes, which we use the symbol A. You might see this referred to as amps. So that's the amount of current. Q is the charge. We measure charge in coulombs. And then T is time. And in this case, we're measuring time in seconds. So you can think of this as an amp is a coulomb per second. That's what this equation is representing here in terms of the units. And then the other important info that we'll use is Faraday's constant, again, which is a ratio 96,485 coulombs per mole electron. So notice we have several ratios here. We've got coulombs per second, we've got coulombs per mole electron. All right, so let's think about when we would apply doing these kinds of calculations. And often the application would be in electroplating, which is an example of an electrolytic cell, or electrolysis we call it. It's when you cover the surface of one metal with another metal. So here's a diagram from our textbook showing an electrolytic cell being used for silver plating. So notice how we can tell in this electrolytic cell in that it is non-spontaneous, so it's non-thermodynamically favorable. And that means it's got a positive delta G, negative cell potential. And we can tell that it's not favorable because notice how there's a voltage source here. So we have to hook this cell up to a battery to force this reaction to run. So it's not a spontaneous reaction. But when we hook this up, we would put our object that we want to electroplate over here at the cathode. And then remember red cat, so reduction is going to occur at the cathode. So in this case, our solution contains silver ions, and the silver ions are going to be reduced to form solid silver at the cathode. So what ends up happening is you end up forming solid silver, and it forms this coating on the object that you're trying to electroplate there. And some purposes of why you might do that, one would just be appearance, for decorative purposes. Another reason might be for protection. So maybe you might have a metal that's that is easily oxidized and maybe would like rust easily, and maybe you want to put a coating on it to inhibit corrosion. So that's another possibility. Jewelry could be plated to give a silver or gold finish to it. Okay. So thinking about these values that I mentioned earlier, notice we mentioned a few ratios. So we mentioned that an amp is a coulomb per second. And that we have another ratio here. So here's the one ratio, amp is a coulomb per second. Then we said Faraday's constant is it's 96,485 coulombs per mole electron. And then another ratio that we'll see is when we look at the balanced half reaction, this tells us the ratio of moles electrons per mole element. So this is another ratio we will know. So here's an example so you can see what I'm talking about. Like let's say this is our half reaction. your aluminum ions are being reduced to form solid aluminum, I can tell from this balanced chemical equation that we need 3 moles of electrons per every 1 mole of aluminum here that we are forming. I guess this is probably the aluminum we care about, but okay, there you go. So this is a ratio of moles electrons per mole aluminum. So the reason why I'm pointing this out is I want to point out that every time you have a ratio, you can think of that as information that can be used to convert from one unit to another unit. So like if we know the amount of time that has passed and we know the amps, we could figure out coulombs. So like an amp is a way to convert between coulombs and time, essentially. And then if we know coulombs, we could figure out moles of electrons because Faraday's constant tells us the relationship between coulombs and moles of electrons. And if we know moles of electrons, we can find the moles of element that we're producing, and we get that ratio from the balanced half reaction. And then if we know moles of elements, we could also find grams. Like if we want to find how many grams of aluminum did I coat on this object, for example, and then we would use the molar mass from the periodic table, and that's in grams per mole. So this might remind you a little bit of stoichiometry. We're thinking of a little dimensional analysis. You want to consider what value you are given and what you're trying to find, and think about how you can use these various relationships to get you from point A to point B. So we could, given time and current, we could find coulombs and moles and even grams. Or if we're given grams, we could work our way backwards and figure out the coulombs. We can maybe find the current if we knew coulombs and time. So there's all sorts of variations of problem solving that we can do involving these key ratios here. Really, it comes down to these key things here. The current is the coulomb per second. Faraday's constant is the coulombs per mole electron. And then our balanced chemical equation will tell us the relationship between moles of electrons and moles of the thing that you are electroplating, like maybe silver or copper or nickel or whatnot. So let's look at 2 sample problems so you can see how this might work. So here's an example. We are electroplating silver onto a spoon here, and we want to know how long it would take to plate out 3.56 grams of silver from a solution containing silver plus 1 ion. So we want to consider here's the reduction reaction that's happening here. And this tells us that there's 1 mole of electrons per every 1 mole of silver that is plated out. So that's telling us the electron to mole silver ratio. And then we know that the current is 2.5 amps. And the key thing is that whenever you see a current in amps, you want to recognize that that is an amp is a coulomb per second. So there's 2.5 coulombs for every 1 second. And then another relationship we know that is not given to us in the problem because they're assuming that we know it already, like from our equation sheet, is Faraday's constant, so 96,485 coulombs per mole electron. So here's all these relationships, and I'm trying to find how long. So I'm trying to solve for time. So I'm going to start out my calculation with the one value I'm given that's not a ratio. So I'm going to start out here with my 3.56 grams of silver, and I'm trying to get to time. And so if I can work my way backwards, I notice how I can figure out time if I just knew coulombs, and I could figure out coulombs if I knew moles electrons, and I could figure out moles electrons if I knew moles of silver. So my first step is I'm going to convert grams of silver into moles of silver. So I'm going to look up on the periodic table. I think 1 mole of silver is about 107 grams, and then I'm going to convert moles of silver to moles of electrons. So I know from my balanced half reaction here that every 1 mole of silver needs 1 mole electrons to reduce it. And then I always know the relationship between moles of electrons and charge because that's a constant. So that's coulombs. And then if I know coulombs and I know the current tells me the coulombs per second. So I could say, okay, and there's 2.5 coulombs per second. So I set this up using some dimensional analysis to get me from grams silver to moles electrons to coulombs to finally seconds. So when I stop and solve, my answer here is going to be seconds. So if I look back here at this visual, what I did is I kind of worked my way backwards here. I started at grams, I went from grams to moles, then to moles electrons, to coulombs, to time. And there's different strategies that you can do to solve this. I tend to set it up as one big dimensional analysis problem, but you can break it down into like several mini steps and solve it that way. But the process will be the same. You're using these ratios to convert from one unit to another unit. Yeah. So you're going to stop and solve here. And if I plug that in my calculator, I will do this real quick so you can check your work. So stop and plug this in your calculator, and we can compare answers. By 107 times 96,485 divided by 2.5. So that's 1,000. How many sig figs? Let's see. I think I just have 2 sig figs. So I said 1,000. It was 1,284 seconds. So I just rounded to 2 sig figs. That's a lot of seconds. I'm going to divide it by 60 to turn it into a unit that's maybe a little more reasonable. So 21 minutes would be how long this would take. Okay. They didn't specify in this case what units the time should be in, but you want to be careful. If the question asks you how many seconds or how many minutes or how many hours, make sure you're reporting your answer in the correct units and that you're, of course, like labeling your units in your work and in your answer. All right, here's another example. In this case, we got an electroplating of nickel. We've got 40,000 coulombs, so 40,000 coulombs of charge is passed through a solution of nickel sulfate. So nickel sulfate, if we look at that chemical formula, nickel sulfate, we know that sulfate has a -2 charge. Therefore, it looks like nickel must have a +2 charge because these charges must add up to 0 because this compound's neutral. So what's happening is my aqueous nickel ions are being converted into solid nickel. And so I can figure out that each nickel must take 2 electrons because I can look at the charges here. So it starts with a +2, add 2 negative things to it to make neutral solid nickel. Okay. So we know the relationship here is 1 mole of nickel per every 2 moles of electrons. So that's why it's important to know the balanced half reaction here. We know the coulombs. We're trying to find mass of nickel. And let's see, what else do we know? We know the 96,485 coulombs per mole electron. Okay, so let's start working through this. So again, I'm going to start with my one value that is not a ratio. It's just a number by itself, which is this one, 40,000 coulombs. And then what can I do with that? Well, I know the relationship between coulombs and moles electrons. So there's 96,485 coulombs per every 1 mole of electron. So if I were to stop here, my answer would be in moles electrons. And I want to find mass of nickel. So that means I want to go from moles of electrons to moles of nickel. So this chemical equation tells me that I need 2 moles electrons for every 1 mole of nickel. Okay, so now I'm at moles of nickel. And then the last question says, last part of the question is, what is the mass there? So I'm going to look up on the periodic table. I don't have a periodic table in front of me. And so I'm going to figure out what the molar mass of nickel is. Actually, I do have a periodic table. Okay, it's 58.6. There you go. So that's another ratio. It's the grams per mole. So if I stop and solve here, I would have my answer. So 40,000 divided by 96,485 divided by 2 times 58.6. This would be 12 grams. I'm kind of unclear on the sig figs on this number here, so I'm just going to go with 12 grams as my answer. Notice how this problem did not involve current at all. So time was not mentioned, current was not mentioned. We just went from coulombs to grams. So in this case, we started at coulombs, and we did 3 steps here to find grams. So those are some examples of applications of Faraday's constant and current and how you would use those values here that again are given on your equation sheet. This is not something you have to memorize, but you just do want to practice with this so you feel confident in how to problem solve here. All right, reach out with any questions that you have.